My name is Ramesh HG, Assistant Professor of Mathematics, Government First Aid College, Tiptur. Today I am going to prove two theorems and some problems and some properties about subgroups. In previous class, I have already explained what are subgroups, what are groups, and their examples. So, group means an algebraic structure with one or two binary operations is called an algebraic structure. Group means an algebraic structure with a binary operation star is called a group if it satisfies the following properties: closure, associative, identity, and inverse property. And if it is called as an abelian group if it satisfies commutative property also. So the examples for groups are set of all integers, set of all rational numbers, set of all real numbers, set of all complex numbers. So these are all groups under addition. And set of all integers is not a group under multiplication as it does not satisfy inverse property. Set of all non-zero rationals, set of all non-zero real numbers. So these are group under multiplication as they contain inverse elements. One acts as identity element in non-zero rationals, non-zero real numbers, and each and every element has its own inverse, and hence they are infinite groups. The fourth roots of unity and the cube roots of unity are the two groups, are the two finite groups as they satisfy all the properties of groups. And next we come to subgroups. So a non-empty subset H of a group G with a binary operation star is called a subgroup if it satisfies all the properties of a group. Then it's called a subgroup. For example, if you take set of all rational numbers Q and set of all integers. So set of all integers is a subset of set of all rational numbers, and set of all rational numbers is a group. Set of all integers is also a group. Therefore we say set of all integers is a subgroup of set of all rational numbers. Similarly, set of all real numbers and set of all rational numbers. Set of all rational numbers is a subset of set of all real numbers, and both are groups. Therefore, set of all rational numbers is a subgroup of set of all real numbers under addition. Both are additions. So these are some examples for subgroups properties. And if you take set of all integers, so the multiples of 2, multiples of 3, multiples of 4, like that, all are become subgroups. So multiples of 2 means it contains 2, 4, 6, 8 and so on, 0, minus 2, minus 4, etc. That is a group as it satisfies all the properties. 0 acts as an identity element. Inverse of minus 2 is 2, inverse of minus 4 is 4. Inverse of 6 is minus 6, like that, it satisfies all the properties. And multiples of 3 is 3z. So minus 9, minus 6, minus 3, 0, 3, 6, 9, etc. It also satisfies all the properties of group, and hence it is a subgroup of Z. So all are subgroups of Z, 2Z, 3Z, 5Z, 4Z, 8Z, all are subgroups of Z. And if you consider finite groups, that is fourth roots of unity, 1 minus 1, I minus I. And if you take set H is equal to 1 minus 1, then it forms a subgroup under multiplication. So these are some examples of subgroups. Next we come to the two properties of subgroups. Two properties of subgroups. First theorem is a non-empty subset H of group G is subgroup of G if and only if AB belongs to H, A star B belongs to H, and second one is A belongs to H and inverse belongs to H. Suppose H is a subset of a group G, then it becomes a subgroup if it satisfies these two properties. So assume that first step H is a subgroup of G, assume that H is a subgroup of G, then it clearly satisfies closure associative identity and inverse property. So the first one is closure, second one is inverse. So automatically it satisfies these two properties. Case 2, if H satisfies these two properties, then you want to show H is a subgroup. So this is closure, this is inverse, this is closure, this is inverse. Then you have to show that it satisfies identity property and associative property. So this is closure, this is inverse. You have to show identity and inverse, identity and associative property. So first one is closure, second one is inverse. So A belongs to H, A inverse belongs to H, A into A inverse by first property belongs to H, so E belongs to H, and hence it satisfies identity property, and associative law is satisfied because H is a subset of G, and hence H is a subgroup of G. So this is clearly easiest proof. So if H satisfies, if H is a subgroup of G, then it satisfies these two properties, then it becomes a subgroup. Second one is a non-empty subgroup H of a group G is a subgroup of G if and only A belongs to H, B belongs to H, then AB inverse belongs to H. This is a property. A belongs to H, B belongs to H, then AB inverse belongs to H, A star B inverse belongs to H. So this property is equivalent to 4 properties, that is closure, associative, identity and inverse property. This is equivalent to 4 properties or 3 properties is a closure, identity and inverse property, because associative is satisfied already in G and hence it is satisfied in H. So we have to show that from this property, closure, identity and inverse property. Let case 1, let H be a subgroup of G, then it satisfies the condition. How A belongs to B, A comma B belongs to H, then A comma B inverse, because H is subgroup, so B inverse belongs to H. Therefore A comma B inverse belongs to H, A into B inverse belongs to H, A star B inverse belongs to H. That is first part. Case 2. Let H is a subset of G and satisfies this condition. AB belongs to H, AB inverse belongs to H. So from that property you have to show all the properties. So A belongs to H, A inverse belongs to H, then A into A inverse belongs to H. That is identity element here. A belongs to H, B belongs to H, A belongs to H, and it is B inverse belongs to H. Then A star B inverse whole to the power of -1 belongs to H. So and hence A star B belongs to H. Associative law is satisfied and hence H is a subgroup of G. So this is one of the important property of subgroup. So if H is a subgroup of G, then A comma B belongs to H, A star B inverse belongs to H. Next examples, the set of all even integers with 0 form a subgroup of G of all integers. So even integers, that means multiples of 2. So it contains 0, 2, 4, 6, etc., -2, -4, -6, etc. So that forms an abelian group under addition. So 2Z is a subgroup of Z. So multiples of 3, you take multiples of 3, multiples of 4, multiples of 5, etc. All are subgroups of Z. The set of all multiples of 5, that is 5Z with 0, forms a subgroup of group of integers. So this is another subgroup. Here you consider G fourth roots of unity. 1 minus 1 I minus I is a group under multiplication. Let's write all the subsets of G. So here we have to write all the subsets. So these are the subsets: 1 minus 1 I minus I, 1 minus 1, 1 minus 1 I, 1 minus I, minus 1 I, minus 1 minus I, etc. So these are all the possible subsets. So from these all possible subsets, first one is 1. So this is become a subgroup of G. This one is subgroup. This one is subgroup. This one is subgroup. So first one is subgroup, and this one is subgroup, and the last one is subgroup. Are the three subgroups of G. Because 1 into 1 is 1, so it satisfies closure. Identity element inverse of 1 is 1, so and density is a subgroup. 1 minus 1, so 1 into 1 is 1, 1 into minus 1 is minus 1, minus 1 into minus 1 is 1, so it satisfies all the properties, and hence it is a subgroup. So in this table we can clearly show that, so it satisfies all the properties of subgroups. So all are elements of G, and hence one acts as identity element, and inverse of 1 is 1, inverse of minus 1 is minus 1, so it satisfies all the properties of group, and hence it becomes a subgroup. So it's a group structure. So 1 minus 1 I minus I, 1 minus 1 I minus I, all are elements of G, and one acts as identity element, and inverse of 1 is 1, inverse of minus 1 is minus 1, inverse of I is minus I, inverse of minus I is, so it is a group structure, and 1 minus 1 is, so this table shows that it is a subgroup. This table shows that it is a subgroup. Okay. And here Z, it consisting of numbers 0, 1, 2, 3, minus 1, minus 2, minus 3. 2Z, it consists of even integers, and 3Z, multiples of 3. These are the subgroups of Z under addition. It is clearly under addition. So in this way we can say that a non-empty set H of a group G is a subgroup if and only if it satisfies one property, that is A comma B belongs to H implies A star B inverse belongs to H, one property, one theorem. And second one is a non-empty set H of a group G is a subgroup of G if and only if it satisfies A comma B belongs to H implies A star B belongs to H, and A belongs to H implies A inverse belongs to H. So these are the two properties. And examples are 2Z, 3Z, 4Z, 5Z. These are all subgroups of Z. And if you consider fourth roots of unity, that is 1 minus 1 is a subgroup of G is equal to 1 minus 1 I minus I, and these are finite groups, and set of all integers and rational numbers are infinite groups. So this is some basic ideas about subgroups and their properties. Thank you.